Great. So really what I'm going to do now is just give you an idea more or less of what's involved in having sort of a explicit and modal analysis or free response kind of approach. Unfortunately, I'm going to show you this in Octave, so this is going to be different programming language, but the important thing is I'm going to highlight sort of a concept here. So don't worry about the details. It's not about the details. It's not something you're going to have to be able to reproduce. It's really something to leave you with in this course to say, if ever you want to do dynamics in finite elements and you need to do something on your own behalf, on your own volition, or try to code something, this is to convince you that it's not that involved. Follow the maths and you'll be in a good place. So this is really the spirit of what this is, okay? And it's more just to illustrate it and to supplement a little bit the video that you watch after this video that sort of is a bit more practically orientated within an environment, but shows you some really nice examples. So here the examples are very simple and trivial on purpose so that we can just check a couple of things, common sense things. Okay, so what this entails is essentially we have, I've got here a quad-4 dynamic free response function that I've written. Essentially, this thing starts off by loading all the data from a finite element analysis. So this is now sort of a finite element model that sets up the mass matrix, that sets up the stiffness matrix, and then sort of I've defined sort of initial velocities and initial displacements for each free degree of freedom in that system. So that's essentially, in order to start a free response, we need to first start off with the initial condition. And those initial conditions will dictate sort of what are, in our free response, kind of what are the values that are entailed there. That is really what that boils down to. Okay, so what those coefficients are, those A and B coefficients that we spoke about yesterday. But that's really what this boils down to. So this loads all of that in initial stuff. And again, take note that each node's X and Y displacement and each node's X and Y velocity needs to be defined. Those are all the free degrees of freedom. So it's large vectors. If a million degrees of freedom mesh into a 2D problem, and let's say it's a million free degrees of freedom, where the other ones have been constrained, you're ending up with a vector of 2 million values just to define essentially the initial position. Another 2 million values to define the initial velocities. That's really what that boils down to. But bottom line is this loads all of this initial stuff, as well as the eigenvectors that are involved in the system. And all that we do is as simple as this. We set up our initial information. So this is really what this x0 and v0 is what was loaded now. It sets up that initial information. Well, actually, I'm not even using that. I'm just using it directly here. So I use this initial information here to solve a least squares problem to define those coefficients A and B. That's really what it is. And this is that linear version where the coefficients are linear in those vectors. So that's the version that we looked at secondly, the second version we looked at yesterday, the one with the A cosines plus B sines. It's that version that we are looking at, where those coefficients are defined. Once we have solved this for the initial conditions, we're done. Now we just step over time and over the eigenvectors, the number that we choose. We can choose 1, 5, 10, depending on what we want to do. The more we choose, the more detail we have in the simulation, the longer we wait as well. But then I just evaluate at any time this expression. That's it. I just evaluate the expression and I get the values. There's no integration that's happening and nothing. Just evaluating at any time, at 1,000,000 times seconds or 10 times seconds, doesn't matter. It will then essentially compute the updated velocities and displacements. That's it. And then in the end, this all just plots it. That's really what this does. Okay, so let's look at how this looks before we go to the next one. So this one, essentially, if I run this, make sure I can get these figures sorted out. So let me just run this. I'm going to run this with 5 modes. I'm going to just choose 5 modes. And so what you'll see here is essentially, I get figure 2 to respond here. So there's that figure 1 is active. That is good. Figure 2 is not working at the moment. This is a pity. So I'm going to make this figure. So you can see here. Oh. Okay. Let me make this figure. Sure, this is now confusing. Okay, so all I want to show you there is if you look at this figure here, so it's a little bit, let me just delete this one. This one is now causing havoc. All I want to show you here is essentially that beam is now oscillating up and down. Didn't look quite like that in the plot, but essentially that's what's happening. And here you can see the difference in energy in terms of strain and kinetic energy, and you can see there's no work being done, but the combined strain and kinetic energy is always a constant. This is what you see here, as there's no damping in this free response. Okay, so this is really just to confirm the stuff that we spoke about yesterday, visually show you numerically what's going on. Okay, that's what that's doing. Now I'm going to run essentially, well, I'll just run. Let's first discuss the next aspect. Oh, I think I would have had a problem here. Okay, I might have spoken the previous one over that text. Okay, hopefully that was visible. Okay, so that is the free response. That's it. Now we're going to go to the integration one, the direct integration approach. And what I just want to demonstrate here at this stage is, and I'm not going to run it necessarily. It's going to run the same way. I just want to show you. Well, maybe I'll just quickly run it so you can see that it does work. But all of this is involved here is that CFL condition that we spoke about, the beta parameters for our new mark scheme, and that we want to do. Essentially, that choice would dictate a certain kind of scheme. Here we choose essentially an unconditionally stable scheme. If we had chosen an explicit scheme, then essentially we would have had to read what the CFL condition. I'm going to show you what the time step would have been for an explicit scheme, that you understand what is the order of differences in time steps. Here we can choose any time step and it will work, but we always start at 1. Why? Because we start with the initial conditions. This is what this says. If time is 0, we start with the initial conditions, and then we have to integrate. And for all the other time steps, we do this else part. We just integrate. And this integration involves a matrix that needs to be constructed. And the detail is not important. The only thing that you need to understand is it's made up of a stiffness matrix, actually a mass matrix, and a stiffness contribution. So if, for instance, I choose an explicit scheme, this contribution here with beta would be 0. This would fall away. I would only have the mass matrix. Then if I have a diagonal mass matrix, this inverse that's computed here. So this is solving a linear system. This backslash is just essentially saying the inverse of A. But this is really what this is. If that's a diagonal matrix, the inverse is 1 over the components in the diagonal matrix. Very easy to compute, efficient. Okay? And that's why explicit integration has essentially always diagonal mass matrices, because this step is then very fast. If I have an implicit scheme, so implicit where this beta is not 0, but some value, then I have a stiffness contribution. This matrix is dense, and I have to actually solve a linear system or compute the inverse of that whole matrix, full dense matrix. This is an expensive step. And so what you'll see is explicit time integration, quick steps, fast, efficient if you have a diagonal mass matrix. Implicit integration schemes, slow steps, but I can have large time steps. It doesn't mean it's more accurate, it just means it's stable. So that's really what that implies. And I continue with this process for each of the time steps. So the problem with the direct integration schemes is we have to start at the beginning. If I want to know what's going on in a million seconds, I have to integrate from 0 to a million seconds. That's the problem. So really understand the difference here. This is really what I want you to take home from the course. Nothing more. You don't have to be able to do this in Python. None of that. Just conceptually understand and appreciate what is entailed. That just to be able to bounce off a little bit when you make decisions. That you are not just making decisions based on stuff in the air, but on concrete, just a little bit of insights on that. Okay, so let me quickly run this one so you can also see how this one runs. See if I can get this thing working now. Oof. Let me get my figures back up and running. I don't know which figure I'm showing now. Figure 1. So here you'll see that beam I'm supposed to displace now. Oof, what is going on here? Actually I have an issue now. So let me just quickly close all of these windows rather. I'm going to have to start from scratch. Okay, let me run it again. This is a small glitch on my side. Okay, that's it. It's supposed to run now. Okay, so there's stuff running. Let me show you in this side the figures. Figure 1, figure 2. Can I actually see these figures somehow? Oh, this is now a disaster. Okay, look, I'm not going to worry about this now. This is, don't want to waste time. For some reason it's now again. Go clear all. Close all. Dynamic analysis. Now it's going. Let me just make sure I can get this running now. that these figures are now shown, figure 1 and figure 2. Okay, so this is just showing you again the beam vibrating here. I'm just going to use this one figure to demonstrate this. You can see this beam is going up and down as we do this time stepping. And then essentially we see, if I can get figure 2 up and running. No, I can't get figure 2 up. For some reason figure 2 is now problematic. But the energy stays the same, the combined strategies and all of that stays the same. Unfortunately this environment is a bit messy working with these multiple windows. That's not in a nice environment. Okay, so that's that aspect. The last thing I just want to talk about is how do we compute these eigenvectors and eigenvalues in a for this generalized eigenvalue problem. This is what this last step is going to be talking about. Quickly see if I can get this on the screen. That's it. And this is the last part of the video, which is just I want to show you. Essentially, I'm doing example 11.2. We've got the mass matrix and stiffness matrix from that example 11.2. Here I compute then the generalized eigenvalue problem with two matrices that I supply, and it's essentially in scipy.linelch.ih. This is all I need to do, done. Now I've got eigenvectors and eigenvalues that are for the generalized problem, and I'm just plotting them for you here. And please go and critically compare them to the values in the book, and you'll see they're spot on. They're on top of each other, and this is the associated eigenvalues. And so this is for that system that we have. Okay, so you can see that essentially this it's extremely high frequency. I can't even recall what the textbook. Let me just see quickly what the textbook's eigenvalues were. I think they only plotted the eigenvectors. No, I can't recall if they discussed the eigenvalues. Yeah, the eigenvalues you can see are also spot on from what you had in the textbook. So you'll see essentially on page 435 in the textbook, all of those correspond nicely. But you can see essentially that is quite high frequencies. But it's a bar that's sort of that is fairly stiff when you try to think about the vibration of that bar along its axis. Okay, that's it. And hope you've enjoyed the course. This is all the formal content of the course. Tomorrow I'll just do a quick review. But please go and watch the other video. Skip over the steps that are related to the nonlinear stuff. But I think it will give you a good idea of what I would like you to take home from this course from a dynamics point of view. So it might run slightly over a couple of minutes for this lecture, but tomorrow's lecture will be shorter. I promise you tomorrow's lecture will be shorter, so we'll make up the time in that lecture. All right?